Inside a sealed cleanroom in Japan, a robotic arm spins a silicon wafer and coats it with a thin film of liquid so pure that a single stray particle can ruin a chip worth thousands of dollars. That liquid is called photoresist, and without it, not one of the chips in your phone, your car, or the servers running the internet could ever be made. Almost nobody outside the industry has heard of it. Yet roughly 90% of the world's supply traces back to just 3 companies, all of them Japanese. To understand why 3 factories hold this much power, you first have to understand what photoresist actually does. A modern chip is built by stacking dozens of microscopically thin patterns on top of each other, layer by layer. Each pattern is drawn not with ink, but with light. And the surface that captures that light is photoresist. Here is how it works. The wafer is coated with this light-sensitive chemical, then exposed to a precise beam of light projected through a stencil-like mask. Wherever the light lands, the chemistry of the resist changes. A developer solution then washes away either the exposed or the unexposed parts, leaving behind a pattern far finer than any human hair. Etching tools cut into the exposed silicon, and the cycle repeats again and again until billions of transistors are sculpted onto a fingernail of silicon. The catch is purity. The features on a leading-edge chip are now just a few nanometers across, smaller than a single virus. At that scale, a contaminant measured in parts per trillion can short a circuit. The metals in the resist must be controlled to levels so extreme that the chemistry has to be cooked, filtered, and bottled in conditions cleaner than an operating room. Making photoresist that performs at this level is not a matter of following a recipe. It is decades of accumulated, jealously guarded know-how. And this is where the story turns uncomfortable. The most advanced chips on Earth are made using extreme ultraviolet lithography, a process so difficult that only one company in the world, the Dutch firm ASML, can build the machines for it. Those machines cost hundreds of millions of dollars each. But an EUV scanner is useless without a photoresist designed to react to that exotic wavelength of light. And almost no one outside Japan can make EUV-grade resist at the required quality. So who are these 3 companies? The first is JSR Corporation, long one of the dominant suppliers of advanced photoresist, so strategically important that the Japanese government itself moved to take it private in a deal worth billions. The second is Tokyo Oka Kagyo, a firm that has specialized in this chemistry for over a century. The third is Shin-Etsu Chemical, a quiet industrial giant that not only makes resist, but also produces the silicon wafers the chips are built on in the first place. Between them, these 3 control the overwhelming majority of the global photoresist market, with the share rising even higher for the most advanced grades. This is not a coincidence of geography. It is the result of Japan spending decades building a dense ecosystem of specialty chemical expertise, where suppliers, equipment makers, and chip factories refine the process together, year after year, in a feedback loop that no rival has managed to replicate. To see why that ecosystem matters, follow a single batch of EUV resist. It begins as carefully synthesized polymers and photoactive compounds, blended in precise ratios. It is filtered repeatedly to strip out particles down to the molecular scale. Then it is chilled, sealed, and shipped under tightly controlled conditions to chip factories in Taiwan, South Korea, and the United States. From bottle to wafer, the entire global production of cutting-edge logic chips hangs on this chemistry arriving exactly right. Now picture what happens if that flow is interrupted. In 2023, Japan added several advanced chip-making materials, including key photoresist chemistry, to its list of export-controlled goods. Exporters would now need government licenses to ship certain products to certain destinations. On paper, it was framed as a national security measure. In practice, it sent a quiet shiver through the entire industry because it proved something most people had never considered. It proved that a single nation could, with a stroke of a pen, slow the production of the chips that power the global economy. Not by controlling the factories that make the chips, but by controlling one obscure chemical that goes into making them. This is what supply chain analysts call a chokepoint. A point so narrow and so hard to bypass that whoever controls it holds leverage over everyone downstream. So why can't other countries simply make their own? They have tried. American and European chemical firms produce photoresist, and some do it well. But matching Japanese quality at the bleeding edge, especially for EUV, has proven brutally hard. The recipes are protected trade secrets. The required purity demands flawless process control. And chip makers, terrified of yield problems, are deeply reluctant to switch suppliers once a resist is qualified into their production line. Trust in this business is measured in years. There are efforts to change this. Governments are funding domestic materials programs, and the Japanese suppliers themselves are building plants overseas, partly to reduce the political risk of having everything concentrated at home. But these moves take years and enormous investment, and they often still rely on Japanese-developed chemistry and Japanese-trained engineers. Diversifying a chokepoint is far easier to announce than to actually achieve. This is the part of the chip story that rarely makes the headlines. We talk about ASML's billion-dollar machines and Taiwan's giant fabs, and those matter enormously. But the entire pyramid rests on materials so specialized that a handful of factories in one country can quietly decide how fast the world's most important industry runs. Photoresist is invisible to almost everyone who depends on it, and that invisibility is exactly why it is so powerful. The next time you unlock your phone, remember that the chip behind the screen began as a wafer coated with a few drops of a chemical most people will never hear named. A chemical refined to near impossible purity, in factories that took a century to perfect, in a single nation that now holds the rest of the world's technology in a very quiet grip. The most fragile link in modern technology is not a machine. It is a liquid in a bottle.
If you found this deep dive valuable, hit the like button, drop a comment below on what tech mystery we should decode next, and subscribe to never miss an episode.